So maybe I'll get started. Okay, so I just wanted to quickly review what we did last time because it'll still be relevant today. So last week we looked at an abstract IMPA algorithm, right? So something I was calling an abstract AMP. The reason for this name, right, is that it wasn't like attached to any specific kind of estimation problem, right? It was just sort of a random iteration that we analyzed. And that looked like the following. So if we initialize with some h naught that's an n-length vector, then the algorithm recursively calculates the following, right? So ht plus 1 is w times f of t ht minus vt f t minus 1 h t minus 1, right? And so, okay, so this was a GOE matrix, right? Just a like random IID or Gaussian matrix that's symmetric. This guy, the role of this term, right, is to establish like nice statistical properties on the elements of the iterates. And so this guy had a specific form. It was the sum of the derivatives of these f functions, and these f functions, ft, we assume to be Lipschitz, right? And acting, we're thinking of these as Lipschitz functions from R to R, and so it acts coordinate-wise on its input. Okay, and so then the results. Okay, so first I'll state them informally, because I think it's a little bit easier to understand, right? So the main theory for AMP relates the performance of this algorithm to kind of a simple deterministic recursion, right, that characterizes what's going on over here. So kind of the informal results say, right, if we initialize independently of the randomness in the algorithm, for t greater than or equal to 1, and as n goes to infinity, right? So our asymptotics here are just n growing, right? Then the empirical distribution of the iterate at any time t, right, where, okay, so I'm going to denote this p hat ht, where, p hat ht is the distribution that puts mass 1 over n on I equals 1 to n on any of the elements of this vector. All right, so what do we say? Okay, so the empirical distribution of the iterate of the algorithm converges to a normal. Right, where in particular, this variance is determined by the state evolution, right? So where tau t plus 1 squared is just the expected value of ft tau t zt, where zt is a standard Gaussian. Right, so, okay, so this kind of deterministic sequence, this is the so-called state evolution, right? It tells us how the state of the algorithm evolves, right? And in particular, we're going to, you initialize it with some tau 1 squared. That's just like a limit depending on that initialization. Okay. Right, so formally, I'll just write out the results. So in general, the formal kind of theorem statements talk about pseudo-Lipschitz functions, right? So the idea is for any function psi from R to R that's a pseudo-Lipschitz of order k, we get some sort of limit statement, right? So limit as n goes to infinity, 1 over n, sum psi HTI converges almost surely to expected value, where we just, replace these elements with the kind of limiting distribution for their empirical distribution. So this is tau t ct. Right, so kind of, the example, right, is if you take, psi of x to be x squared, then this tells us, something about, the norm of these iterates, and in particular, this norm is going to converge to tau t squared, right? So the idea, right, is that the state evolution tells us about, just the properties of these guys. Right, and I mentioned that the assumptions here are what we need, W is a GOE matrix, again, independent of an initialization. I need some regularity beyond Lipschitz on these FT functions. And then you make an assumption about the initial distribution. So in particular, you can assume that the empirical distribution of F0, H0 converges, to the distribution of some random variable I'll call H, and H has some finite moment is kind of what I need. Okay. So, all right, so that's what we did last time. And kind of the goal of today is to use this to look at the problem of rank 1 matrix estimation. So kind of can we take these results and then say something about an algorithm for a simple matrix estimation problem. Okay. So, all right, so we're going to study rank 1 matrix estimation. Okay, and so the model I'm thinking of, right, is I have some data A that's generated via a spike that I'll call V plus random noise, right? So here, W is a GOE matrix, right? Gaussian symmetric. Theta is some value, some positive constant that controls my signal to noise ratio, right? And here I'm going to think of, my spike V, right, is some random or deterministic vector. For us, we'll just assume it's random, but everything goes through if it's deterministic, so long as you kind of assume convergence of its empirical distribution. So the spike V is, some, I'll say random or deterministic vector independent of W. Okay, for us, we'll assume that it's random, right? And so in particular, I'm going to assume a prior distribution on its elements. So I'm going to assume the elements of V are IID according to some distribution that I'm going to call PV with variance expected value of V squared. Okay, I'm gonna try to use both a lowercase v for the vector and maybe an uppercase v for a random variable, that has the same distribution, right? So I want the expected value of v squared to be 1, right? Where capital V is going to be just a random variable with the same distribution as the signal elements.
Is it 0 mean?
We haven't specified yet. Whether it is or not will complicate things, as it turns out. Okay. So, this model has a lot of applications, right? I don't think I necessarily need to sell that here, right? But like collaborative filtering, right, is an application of this model. Perhaps instead of VV transpose here, you have like a UV transpose or something. But collaborative filtering is a slight generalization. Things like topic modeling in machine learning, right, are basically this model. Things like the hidden clique problem, right, where you have, an Erdős-Rényi graph, and you pick out like some chunk of nodes, and then you attach all of them with probability 1, right, and then you want to find that that hidden clique, right? So something like hidden clique, right? So maybe this will be a good example to write down. Right, so hidden clique, right? So okay, so if you sort the adjacency matrix, then you're going to have like your clique here, right? And all of these guys are going to be 1, right? And then otherwise you got a bunch of zeros and ones floating around. Of course, what you see in practice, right, is just the scrambled version with a bunch of zeros and ones, and you're trying to sort to find the clique, right? And so in particular for a clique C, the adjacency matrix has the form of kind of this this low rank model, right, where you have just V is kind of an indicator function of this clique, right? So this is an example, right, where you have actually some structure here in the spike, right? So in particular, when you think about kind of a IID distribution, this is going to be an IID distribution that puts mass on 0 and 1 only, right? So in particular, the spike is non-negative and sparse, right?
Typically, W there is not Gaussian.
Yeah, typically W here is not Gaussian. I guess, yeah, you can put into equivalence with a Gaussian problem, actually, right? Like a Gaussian matrix where you elevate it or something. But yeah, sorry. So this should be something that gives you the background Erdős-Rényi, but these are equivalent problems somehow in my mind. Okay. So let's talk a little bit just about rank 1 matrix estimation. All right. Okay, so if you want to do, rank 1 matrix estimation, right, a kind of a natural way to approximate or estimate V, right, is to use just the principal eigenvector, right? So, and in particular, you know, the community kind of knows a lot about the performance of the principal eigenvector in terms of recovering V, right? So a natural estimator right, is something like, you know, rho hat, which is the principal eigen vector of this adjacency matrix A, right? So in particular, let's think about a situation where I'm assuming that, you know, this spike appropriately normalized converges to 1, right? So, you know, if we're thinking IID distribution, then this is the condition, right? We've already assumed it, right? Okay, so then, okay, so random matrix theory tells us about a phase transition and the performance of this principal eigenvector, right? So in particular, if we look at, you know, the principal eigenvalue, right, so we'll call this lambda 1 of A, right, then it has kind of two asymptotic behaviors depending on kind of the signal to noise ratio in my problem, right? So in particular, if the signal to noise ratio is small, then, you know, the noise matrix, the W just kind of washes out the signal completely. This principal eigenvalue is going to go to 2, right? All the eigenvalues are going to be, you know, this semicircle law between -2 and 2, right? And so this happens, you know, if theta is in 0, 1, right? On the other hand, this eigenvalue is going to be, you know, kind of set outside the rest if we have theta bigger than 1, right? So in particular, it's going to equal theta plus 1 over theta, right? To give us, you know, kind of a spectral gap between this top eigenvalue and the second largest, right? This tells us something about, you know, the correlation of my principal eigenvector with the signal itself, right? So I might want to look at something like, you know, this inner product between my estimator, appropriately normalized, right? And this is going to show similar behavior, right? You get some nice positive correlation with the signal we'd like to recover if we're sufficiently, you know, powered, and then otherwise, no, right? These two things are orthogonal, right? Right. So okay. So this is nice, right? It says, you know, if the problem has enough signal to noise ratio, this principal eigenvector that we can just find with like some sort of power iteration has a, you know, even if it's not consistent, right? At least it points a little bit in the direction of the signal itself. But okay, so one like limitation here, right, is that at least generally it's kind of difficult to encode sort of prior information on the signal into this sort of spectral estimator, right? So if we just think of the classical spectral estimator, right, this doesn't use any structural information on V, right? So in the case that V is, you know, sparse, bounded, non-negative, or whatever, right? You know, you should be able to do better if you somehow encode those properties into the estimation procedure, right? And like, this isn't, you know, there are many applications where you need to make those sorts of assumptions, right? So like sparse principal component analysis, like hidden clique, you know, stochastic block model, community detection, these sorts of things. Okay, so the last thing I want to mention before I start talking about how we use AMP to solve this problem is that, okay, so we have one estimator that gets us, you know, somehow close to the signal if we're in the right regimes. And we also know kind of the optimal estimator for this problem, at least if what we care about is, you know, mean square error between, you know, the true signal and our estimate, or this correlation with the truth, right? So since we know PV, this, you know, distribution on the elements of our unknown signal, right? Kind of the optimal estimator in terms of mean square error is this minimum mean squared error MMSE estimator, right? So this is the kind of the same sort of proof we did in the case of regression, right? The optimal thing we could do is just find the conditional distribution estimator, right? So since we know, you know, another good, in fact, optimal estimator, in some sense, is the MMSE. The minimum mean squared error estimator, which is given by the following. We'll call it, what do I call it? Mu hat Bayes, right, is the expected value of, we'll call it, we'll look at the estimator of the matrix instead of the spike, right? So, you know, in some sense, if we could just calculate this for many problems, we'd be done, because this is going to give us, you know, optimal error in terms of mean square error and these other metrics, right? But the problem, right, again, is that this is generally not something that we can compute efficiently, right? So, you know, what we're going to try to do essentially is estimate it. One thing that I'll talk about later on, right, is though, okay, so generally not computable, right, at least not, you know, in polynomial time, but we can understand the performance of this estimator, right? So there is computable formula for, you know, like asymptotic Bayes risk, right, by which I just mean this asymptotic minimum mean squared error, right? We know the performance of this estimator even if we can't find the estimator itself. So in some sense, this gives us like a benchmark, right? So this is like the best we can do. So whenever we have an estimator, what we're going to do is kind of compare it to how well, you know, we could do if we were able to actually calculate this guy. Right? And so in particular, right, these kind of computable formula that tell us the performance of this asymptotic Bayes risk, right, these are like the replica predictions and stuff from statistical physics that, you know, we were looking at for the random K-set problem. Right, so again, kind of these predictions by the physicists help us actually understand the performance of the AMP algorithm. Okay, so all right, so what I'm going to do is introduce the AMP algorithm for our matrix estimation problem, and then kind of sketch again, like at least like the first step in how we get the distributional properties that are nice. so okay, so the AMP algorithm that we study is the following. All right, so I update xt plus 1 is equal to a times ft xt minus bt ft minus 1 xt minus 1. Okay, so what I did, right, is, so I'm just looking at the same algorithm we were looking at earlier, except, where we had that GOE matrix, I just plugged in, kind of our data from the matrix estimation problem, right? So, kind of the, okay, so what I want to do is try to look at why or how we might be able to analyze this using kind of the abstract recursion we were talking about earlier. So the first thing I'm going to do is just plug in what A is equal to, right? So this is like theta over n times VV transpose plus W. So in particular, if I plug in A, I get xt plus 1 equals what? Okay, so from the first term, the spike, this is equal to theta over nv times the inner product of v with ft(xt). Okay, and then I get another term that has my GOE matrix and minus VT ft minus 1 xt minus 1. So kind of the idea, the way that we study the properties of this algorithm is by noticing that, okay, well, this term is just exactly the abstract AMP as before. So exactly abstract AMP, right? And then, we also have this additional term, which I'll kind of call like a shift term, right? Okay, so if I want to study the, I want to study like the empirical distribution of the elements of this iterate, right? And so what I know, right, is that, okay, for this guy, like, this vector, I already know something about the empirical distribution of the elements of its iterates. I can just rely on the theory we did last time. So kind of the only thing I need to sort of study here is our shift term, right? So what I'm going to show, so my claim is that, okay, if I look at the empirical distribution of the first iteration, this converges to the distribution of what? So the distribution of a random variable, where that random variable is mu1 times v, where, v is a random variable with the same distribution as my signal elements, plus a Gaussian term, plus sigma 1 z, right, which is, z is standard normal. Right, and so you can kind of like see how I'm going to argue this. Basically, this sigma 1 z is kind of the distribution of this guy, right? And then the shift gives us this this function there, right? So okay, so let me try to argue this.
So that h is x, right?
What? Sorry, say that again.
You have an ht instead of xt.
Yeah, they should all be xt's. I don't see the h though. Yep, I see it. it's like I changed the notation in order to like, differentiate it from the like abstract AMP, but that just means I'm gonna like mix the two notations for the rest of the talk. Okay, so, all right, so in order to make this claim, I have to assume a sort of informed initialization. And what we're going to do now is just assume that we have that, and then I'll talk about later how you actually produce such an informed initialization, right? So I'm going to assume I have an x naught that, let's just say it's equal to, mu naught v plus, well, so let's call this little v. So it's equal to like, a little bit in the direction of our signal plus, some Gaussian noise, right? So here I'm thinking of z as being a normal 0, 1 vector. Right, so independent of my signal v. Right, so, okay, so I'm assuming that I have some initialization that gives me, a little bit of correlation with the true signal, and it otherwise is noisy, right? Okay, so then if I look at x1, right, so this is kind of t equals 0, what do I have? So I have x1 is equal to theta over n, v inner product, v f0, x0 plus w f0 x0. Right? Okay, so kind of there are two terms to study here, right? So if I call this term 1 and this term 2, right? So, okay, so the first thing is I know what to do with 2. So if my initialization is independent of my GOE matrix, right, this is the exact same sort of math we did, last week, right, then W F0 X0 is Gaussian with mean 0 and variance given by, the norm of this guy plus some, deviation term, right? That was like the rank 1 spike term, right? The idea is this guy goes to 0. This guy converges to, what, right? So if, 1 over n f0 x0 squared, now this is going to converge to the expected value of f0. I've assumed, like this is, this is my signal, so it's IID PV. This is IID normal 0, 1. So this converges to f0, where the input is mu 0 times random variable v plus sigma 0 random variable z, right? And so, this term converges to, a Gaussian with this sort of variance, right? So nothing new there, right? The only new thing is that I've assumed this sort of informed initialization. Okay, so if I look at this, this first term, right, what I'm going to focus on is just like 1 over n times this inner product, right? So in particular, 1 over n times the inner product of my signal with f0, x0, right? This is just a sum of, vi f0 times the ith element of this, right? The elements of v are IID Gaussian, or IID PV. This is like IID Gaussian, so I can just appeal to like law of large numbers here and get that this, converges to what? Expected value of v, random variable f0, like same thing here, mu 0, V plus sigma 0 Z, right? Okay, so if I put this together, right, what this says, right, is if I look at the empirical distribution of x1, all right, what do we get? So if I look at this first term, I have theta times my vector v plus this inner product that's converging to this expectation. So if I think about the empirical distribution, right, these guys are converging to v, right? So this goes to theta v times expected value of this, right? V f0 mu 0 v plus sigma 0 z, right? And then my second term is just going to go to a Gaussian random variable with, you know, this variance. Right, and so in particular, you know, my claim was that we get this distribution, and indeed, right, so this is mu1 v plus sigma 1 z, where, you know, mu1 is theta expected value of v, f0 mu 0 v, sigma 1. Right. Okay. And so, like, sort of the you know, the short story is that you can kind of iterate this idea, right? Now I'm assuming, right, my x1 kind of has this limiting distribution, right? And you can kind of make the same sorts of arguments. You know, things will get more complicated because you have the correction term, but you can kind of rely on the theory from the abstract AMP from last time. So this sort of defines the state evolution, right? So, you know, what you can show, right, is that, you know, if you use, so can show by induction that, you know, if xt, you know, has an empirical distribution that's like mu t v plus sigma t z, right, then xt plus 1 is going to have an empirical distribution that's like mu t plus 1 v plus sigma t plus 1 z, where, you know, mu t plus 1 is just exactly kind of this, right? It's theta expected value of v times ft mu t v plus sigma t z, and sigma t plus 1 equals, you know, expected value of ft mu t v plus sigma t z. Right. Sorry, something I should have gotten. Sorry, this goes to this squared. Right. Okay. Right, so that's, yeah.
Should that term be maybe sigma squared, I guess? I mean,
Yeah, I think that yeah, this is, let me make sure. Hold on. Yeah, right, so this is sigma squared. right? And then you take the square root of it to get the, yeah, I believe that's correct. Okay. So then the main theory is basically just proving that this holds, right? Let me take my, it's like a, first day they've turned the air conditioning off in here, and it's like it's pleasant, actually. Let me turn the mic off while I. Hello? Yeah. Okay, main theory says the following, right? So, okay, essentially under similar results, or sorry, under similar assumptions as before, right, so I need independence between my initialization and my randomness, right? I need some regularity on F, and then, you know, some assumption on the distribution of the initialization, right? So under similar assumptions as before, for a pseudo-Lipschitz loss that now takes two values, from R squared to R, what do we get? Well, so we get that the limit as n grows of 1 over n sum I equals 1 to n of psi xti vi, where, you know, this is my original signal, my ground truth in some sense, right? So this is going to just converge to an expected value, where that expected value is psi of mu t v random variable plus sigma t z v random variable. Right, so here, where, you know, v has the same distribution as my signal, is independent of z standard Gaussian. Okay, so let's think about some specific choices of the pseudo-Lipschitz loss, right? So examples might be, you know, you can take psi of Vx to be what? Ft of x minus v squared, right? And then this is going to give us back our mean square error, right? So then our result says that 1 over n times the norm of ft xt minus v squared converges almost surely. I want to say this is equal almost surely. This guy converges almost surely to some function of my state evolution, right? So in particular, it converges to expected value of ft mu tv plus sigma tz minus v squared. And in particular, we can simplify this and this is just sigma t plus 1 squared minus 2 over theta mu t plus 1 minus 1. Right. Okay, so this is nice. It tells us exactly how, you know, in terms of at least mean square error, how well, you know, the iterates of the algorithm are doing in estimating the signal, right? You can also, yeah. So they're in the sigma and the mu, right, over here.
So, but we are free to choose this.
Yeah, so what we're going to do is eventually optimize, you know, in some sense, mu squared over sigma squared is like a signal to noise ratio, right? And so we'll optimize that and use that as the FT. But yeah, in general, you can use any FT you or so desire, right, as long as it's like Lipschitz and these sorts of things. But it turns out that, yeah, it's like if we know the prior distribution on the signal, then there's an optimal FT to choose. Right, and it basically comes from the fact that at least we can approximate this correlation function with pseudo-Lipschitz functions, right, to show that how our estimator performs, right? So this converges almost surely to mu t plus 1 over theta sigma t plus 1. Right. Right? Okay, so this is nice, right? Because it gives us sort of exact asymptotic characterization of how AMP is performing depending on, you know, things like the choice of the denoising function, you know, the prior distribution on your signal, and so on. Right, so the next question, right, is what Gabor was getting at. So how do I choose FT, right? And essentially, you know, what we're going to do, right, is use the fact that mu over sigma is like our signal to noise ratio, and we're going to optimize over that, right? Okay, so, all right, so I'm going to define the SNR as mu squared over sigma squared, right? So define SNR as, I'll call it gamma t, which equals mu t plus 1 squared over sigma t plus 1 squared. So if we plug in the state evolution values, this is theta squared expected value of, okay, let's do this. I'm going to square this expected value. This is V, FT, UT, V plus sigma T, Z squared over expected value okay, so I'm not going to prove this, but it's not too hard to show that if you know PV, right? So this is the distribution that I assume my signal elements are drawn from. You can maximize gamma t plus 1 with what? Well, it's kind of like a per iteration Bayes optimal estimator. So you want ft of input s to be the expected value of v condition on mu t v plus sigma t z. Right, so in some sense, this is like not too surprising, right? So I'm arguing here that at any iteration, you know, the empirical distribution of xt, right, looks like mu tv plus sigma tz, right? So how am I going to update my estimate of you know, of v, right? I'm going to basically like denoise it in some sense, you know. So this says, you know, what do I expect it to be, given that my input is like exactly equal to its asymptotic distribution, right? So ft always acts on xt. Xt exactly has, you know, this distribution in the limit. So it's like, let's just assume it has that distribution now and calculate the Bayes optimal update. Okay, and so now if we all right, so this is, you know, so this now we've kind of, you know, we've chosen in such a way that we like maximize this sort of correlation, right? It turns out that like this is always kind of the denoiser you should use within the algorithm. So even if like the error metric that you care about is actually something different, so maybe like, I don't know, you care about like L1 loss or something, you should iterate the algorithm with this denoiser, and then at the end, you know, you would do something like find the median, right? So kind of the idea is like the algorithm should almost always be run with this, and then at the end you can do kind of a post-processing step. But this is going to be the one that gets you the best SNR at each iteration. So ultimately, you know, you have the best SNR at the end, and you can denoise in another way if you need to. But yeah, so you know, if this distribution is not too crazy, right? This is pretty easy to compute. It's not so hard to approximate either. I mean, like, you know, our engineering colleagues use this denoiser and then, you know, use some sort of Markov approximation if, you know, if you can't compute it exactly. But yeah, in simple, like, you know, if this is an exponential family or something, you can compute this in closed form.
It's much easier than the minimum mid square.
Yeah. Yes, yeah. So this is easier. I mean, it's a one-dimensional thing for, you know, for one, right? So it's kind of like you've, gone from kind of those dependencies down to just a single dimension. And now this is something you can easily find. Okay, so I'll also mention when you use this denoiser, the state evolution simplifies. So state evolution with optimal denoiser. Okay, so if I define gamma 0 to be mu 0 over sigma 0 squared, and gamma t plus 1 to be sigma sigma squared 1 minus mm se gamma t, where think this might be. A little bit, I'm not sure if I was using this. There's no sigma square. This is, okay, I'm not, there's a constant here. There may be theta squared, I'm not entirely sure. I have sigma squared, but that doesn't make sense. So I think that this should be theta squared, but this is a little bit of a question what that constant should be. But okay, the idea is, okay, if I choose this conditional distribution denoiser, then basically my state evolution simplifies in the sense that now we can just study kind of this SNR as it tracks over the iterations, right? And so, okay. So now this gives us kind of a way to compare the performance of AMP to like the Bayes optimal denoiser, right? So kind of our information theoretic limits in the problem. So in particular, you know, what we can show is that, you know, one can show that your state evolution converges in T now, right? So I'm thinking as T grows to the smallest strictly positive fixed point of, you know, gamma equals theta squared 1 minus MMSE gamma. So, okay, so what this kind of says, right, is if, you know, if my state evolution, which is now determined by this MMSE function, right, we're going to converge to a fixed point as T grows, and if it has multiple fixed points, essentially AMP is going to converge to like the least good of the fixed points, right? And that's different from the performance of the Bayes optimal estimator, right? So the fixed point of this equation also determines the performance of the Bayes optimal estimator, but it's going to converge to like the good fixed point in some sense. So if we look at, you know, info theoretic limits, what do we know, right? So okay, so if we want to minimize mean square error, right? So just 1 over n times some estimate based on A, you know, L2 distant from the truth over any estimator, V hat A, right? We know what the estimator should be. You know, we take V hat Bayes of A, which just equals the expected value of V, my signal given my data A, right? So, okay, the problem is we can't compute this, right? But what we can compute, right, is the performance of V hat Bayes, right? So we use it as a benchmark, right? So in particular, it's described as well by the fixed points of this equation. Divided by fixed points of gamma equals theta squared. Right? Okay, and so in particular, you know, it attains a fixed point described by a potential function. Right, and so in particular, we can use these kind of potential functions to describe all the fixed points, right? And essentially what we know, right, is that, maybe I'll write it, as that if there are multiple fixed points, the Bayes optimal estimator is going to find the good ones, whereas AMP will not, right? But if there's only one fixed point, then AMP is Bayes optimal, right? So this is kind of summary of computational versus info-theoretic performance, right, for this problem, right? So what do I want to say, right? So if, you know, SE has only one fixed point, AMP attains it in the T limit, right? And that fixed point also characterizes the performance of the Bayes estimator. Right, so in this case, right, AMP is Bayes optimal. It kind of it attains, you know, AMP Bayes optimal, and there's no statistical computational gap, right, because we have a polynomial time algorithm that matches the Bayes limits. On the other hand, right, if there are multiple fixed points, essentially what's going to happen is, you know, the Bayes estimator finds the best one, AMP finds the worst one, right? And we have this kind of gap between what AMP can do and what we should be able to do optimally. But, you know, on the flip side, this is a problem where, for example, if AMP can't solve it, right? So if AMP is not matching the Bayes optimal performance, then there's no known polynomial time algorithm that can, right? So in this problem, if you know, if there are multiple fixed points, right, then no sum of squares algorithm, no SQL algorithm, no low degree polynomial, right, finds a better performance than AMP, right? So one of the uses of AMP, right, it can be to kind of study problems and see if we see this phenomenon of the computational to statistical gap, right? So these are problems where our known algorithms aren't performing at the rates that we know are possible, right? Sure.
So there are, first you take the limit in n.
Yes.
Then you take the limit in t.
Yes.
So I guess this is,
You can't switch it.
yeah, so are there like finite sample bounds?
Yes. So the first of which I wrote during my PhD. So I'll give myself a plug on that later. Yeah. So I have some finite sample bounds, but essentially like they're almost asymptotic again because you need T to grow very slow relative to N. So like, you can only get concentration for the like state evolution predictions if T is like log N over log N or something really awful. But Yu-Ting Wei at University of Pennsylvania and one of her PhD students have been revisiting this problem in the last year or so. And at least for this low-rank matrix estimation problem, they now get finite sample results for T like polynomial and log N or something. So they've improved it quite a bit.
But T should be small in order to be able to train polynomial time, I guess.
Yeah, so you need, so T, needs to be like, no bigger than like log N anyways or something to, so I think Yu-Ting is able to kind of like clean up these things and actually give some usable bounds, but yeah. Yeah, so when I first like did the finite sample analysis, it's like I just, I did it within the inductive proof, and basically you, at each, induction on T, you degrade the concentration a bit. And so then, eventually that degradation was so much that you get these like, these kind of slow growth. And then she did now the proof methods have evolved a bit. So, hers is more like she studies kind of an idealized AMP algorithm alongside, the real one. And then in that idealized one, you don't have the kind of degradation. And then she shows eventually that they're not too far away. So there needed to be something clever in the way that the proof is remade in order to get the finite sample. Okay, so maybe to wrap up, I'll say something about the initialization. How do we actually do this kind of warm start? Okay, so if we revisit the initialization, you'll remember that I assumed that we had, an x naught that was already like a little bit in the direction of the thing that I'd like to recover, right? So I assume that x naught is like mu naught times my signal v plus sigma naught times a vector z, right? So z is an IID Gaussian vector. Okay, so why do I need to assume this? Okay, so essentially the reason is the following. So let's imagine expected value of v is 0, right? So this says my signal elements have mean 0. And mu 0 equals 0, right? So I have no correlation with my signal. I just, randomly initialize. Well, then if I look at my state evolution, so mu1 is theta times the expected value of v times f0 mu 0 v plus sigma 0 z, right? But okay, I've assumed mu 0 is 0, right? So I don't have an informed initialization. So this is theta, expected value, v, f0, sigma 0, z, right? But I've also assumed that this z is independent of v, right? So this is just theta, expected value of v, expected value f0, sigma 0, z, right? But now this is 0, this is 0 too, right? So mu1 is also 0. And basically what you can do is if you calculate mu2, given that mu1 is 0, then it's also going to be 0, and mu3 is 0, and so on. So what this says is if you initialize in this way, when your signal has a mean 0 elements, essentially you're never going to get any sort of correlation with the signal, right? You're just producing complete noise, right? So, this implies, right, so in this case, right, AMP estimate not correlated with the truth, right? And this is bad, right? On the other hand, right, if this is not equal to 0, then there's actually no problem, right? So if the mean of the signal elements is not 0, then you can initialize with just the all ones vector, and everything's actually fine. So the kind of informed initialization is specific to this case where we have mean 0 elements there. The nice thing is that you can essentially just use a spectral initialization and like your life is good, right? So, okay, so the idea, which as a community, like folks were doing long before we could prove that this was a good idea, but the idea is that if we assume that the expected value of our signal elements is 0, we should use x0 equals rho hat, which is my principal eigenvector. Right? And why, right? Well, we already looked at this, right? Because we know if we have sufficient power, then this is going to give us a positive correlation with the signal, at least asymptotically, right? And that's good enough for all this theory to go through. And so this works in practice, but now x naught equals rho hat is not independent of w, right? So one of the assumptions we had the whole time, right, is we need to initialize independently. And, this is no longer true because this was estimated from A, which obviously has the w in it, right? So in general, like a, standard AMP theory fails, but there's some updated theory by Montanari and Venkataramanan in 2020 that essentially say like life is good anyways, right? And kind of the interesting thing is the AMP algorithm, in some sense, is like a generalized kind of power iteration. So you can even like find this principal eigenvector by running AMP with a certain denoiser for some time, right? It's basically like doing a power iteration. And then after that amount of time, you have, enough correlation that you can start running AMP with like the conditional distribution denoiser. And so, that's like what people are doing in practice.
So in this particular problem, how does AMP perform with respect to visualization?
Yeah, so like I'll give an example. So you mean like in terms of like the computational statistical limits, or?
No, you said that there's a phase transition for the principal eigenvector when theta is less than 1, then it's impossible.
Yeah, okay. Yeah, so if theta is less than 1, AMP I don't think gets you doesn't buy you anything. You still need to be sufficiently powered so that, this okay, so let's see. I Okay, so I just want to give like one quick example about just when AMP is performing at the Bayes optimal limits and not. So let's imagine, our signal elements are Rademacher plus minus 1 with equal probability, right? Expected value of v squared is 1. Expected value of v is 0, right? So this is a situation where, AMP with spectral initialization is Bayes optimal. Right, so it matches performance limits of v hat Bayes. Right, but if we just change this prior distribution a little bit, so now let's say, I take values minus C1, C2 with probability, E, 1 minus E, such that expected value of v equals 0 and expected value of v squared equals 1. Right, this is a situation where, state evolution has multiple fixed points. Right, which means that there's a kind of a statistical computational gap, AMP not Bayes optimal. And in fact, right, like strictly worse than Bayes optimal. So, yeah. Yeah. Yeah, so if you don't, so if you don't know PV and theta, okay, you can still run AMP and actually, okay, so now you wouldn't be able to characterize the state evolution, right? Because that, for example, depends on PV and theta. But what the theory tells you, right, is that xt squared, this is going to converge to something like mu t squared plus sigma t squared. It might be not exactly that. But essentially what you can do is you can just run the algorithm and then use kind of the norms of the iterates itself to approximate its own state evolution values. And so then you can kind of know the performance of you can approximate these sorts of state evolution values. So you can know in some sense how AMP is going to run, even if you don't know those guys. I'm not quite sure about the information theoretic characterization of the Bayes optimal estimator in that case. But yeah, you can still kind of, IMP allows you to use its own iterates to approximate its state evolution and these sorts of things. So, okay, so I just, to wrap up, I wanted to mention a few extensions of this abstract AMP. And, the reason being it'll be, it's through these extensions that, we'll get the AMP that we'll talk about on Wednesday. So, okay, so I first just wanted to mention that there's a non-symmetric AMP. right? So this is sort of like if instead of being GOE, our W matrix is like M by N, and it's IID, normal 0, 1 over M. Right, so this says, like, what if the matrix is not GOE, right? It's no longer symmetric, it's just IID Gaussian. Essentially, the idea is now you have a two-step iteration, right? So, you know, B0 through BT or N R M, H1 through HT or N Rn, right? And you get this kind of two-step thing. So like BT equals W FT HT minus lambda T GT minus 1 BT minus 1, right? And HT plus 1 equals W transpose GT BT minus psi T FT HT. Right, so, okay, so now you have you have to do kind of two steps at each iteration. They're symmetric, like these lambdas and psi's are like, sums of the derivatives of the denoiser functions. Now you have two denoisers that you have to choose, and so on. You can write out the state evolution. Now there's two terms, right? A sigma term that depends on the G's and a tau that depends on the F's. And then like all the theory more or less goes through exactly as the abstract AMP, but now we have a non-symmetric version. There's also, a matrix version. So a matrix AMP, right? Where now like BT and HT are matrices instead of vectors. Again, like everything is pretty like predictable, like what the algorithm looks like, what the state evolution looks like, what the theory gives, these sorts of things. The major tool of the matrix AMP is that you can reduce the non-symmetric AMP to the symmetric AMP through a matrix AMP, right? So, the matrix version allows you to go back and forth between the symmetric and non-symmetric versions. But kind of the idea is that, with all of these things, you reduce it down to the abstract AMP in some way, and your proof starts there. So I'll mention finite sample results. So, finite sample. Okay, so, like kind of what happens in the large but finite regime, right? All my results are asymptotic. These Lipschitz losses were converging to deterministic limits given by the state evolution. So the question is, can you show concentration of, those pseudo-Lipschitz losses around their state evolution prediction? And it turns out yes, under like some stronger assumptions. So the first work was Rush and Venkataramanan. Unfortunately, so this was like 18, I think was the final paper that came out. Right, so, it's a state evolution concentration, but you need, T like log n over log n iterations, which is very slow. It's like AMP converges quickly, but that's not that quickly. And then recent results by Lee and Wei This is 22, and Lee, Pan, and Wei, and 23. Now they can get, at least for this rank 1 problem, they can get, T like n over polylog n iterations. So much quicker sort of rates. So this is for rank 1 matrix estimation. Okay, so I'll wrap up there, and then on Wednesday I'll talk about AMP for like generalized linear models. So these are solving, these function estimation problems using things like regularized least squares, like lasso, and those sorts of things for high dimensional predictions. So yeah, that'll all, there we kind of need this non-symmetric version of the AMP algorithm, because these are not naturally symmetric problems and these sorts of things. So that's the plan for next class. Happy to take questions. If not, we can go to lunch.